Hello, everybody. So this presentation is about partitions and scheduling and how to run effectively on Graham and Cedar. So what are partitions? Well, they're somewhat like user classes in PBS, Torque, and Moab. So your job will automatically be assigned to a partition on Compute Canada systems. A job can be in multiple partitions simultaneously, and the job can have multiple partition priorities. A node can be in multiple partitions simultaneously. So unlike a queue, your job can have multiple partitions, and nodes can be in multiple partitions. So effectively, the mechanisms change a bit. But it does what a queue does in most other scheduling systems. So we're going to be discussing partitions, and we'll do it with some Venn diagrams. So for those that don't know, Venn diagram is basically a diagram that shows properties. In here we have a very simple one. Has only two legs here in blue, and you see that kangaroo, ostrich, eagle, crows, and sparrows have only two legs, and can fly is in red. Crows, butterflies, sparrows, and bees can fly. But there's ones that are in both, like the crow and sparrow, right? So we're going to use this to show how partitions work. So let's look at a simple partition Venn diagram here. Now this is an imaginary 5-node cluster, and these particular Venn diagram is just an example. The Compute Canada systems don't work this way, but at least in terms of GPUs, the Venn diagram partition though is accurate. We're just doing a simplified diagram first to understand what's going on, and then we'll move to a more complex what's actually happening on Graham and Cedar. So we see here basically two circles, and we see that the blue circle is totally within the red one. So we have a red partition, and we can think of this one. In this example, it has CPU cores, and a blue partition that has GPUs. And we see that every single one of these dots is a node, and we see that everything in the blue partition is also in the red partition. So we see that there are basically 5 nodes in black, and there's 5 nodes in the red partition. So these nodes are both within the red and the blue. There's 3 nodes in the blue partition, and they're also in the red partition, right? And there's 2 nodes that are in the red partition but aren't in the blue one. So in this case, they would have CPUs, cores, but not GPUs, as an example. So a job that requires CPUs, in this example, a red partition can run on any of these 5 nodes. But a job that requires GPUs can only run on any of these 3 nodes. So let's go one step further. Let's bring in idle and busy nodes. So let's make the idle nodes in green circles, and the busy nodes in yellow circles here. Well, in this case, we see that there's 2 idle nodes in the red partition and none in the blue partition. So a job that requires a GPU node from the blue partition will be unable to start if there's no GPU nodes available. Jobs that require CPUs only, or jobs that require the red partition, will be able to start immediately, even when there are higher priority jobs that require the blue partition, right? So in here we could say that, that there are 2 idle nodes in the red partition and jobs can start immediately there. So in addition to this, these Venn diagrams, we're going to start with some other information here. As you may know, there's actually 7 types of nodes on Cedar. We've divided them into basic type of nodes. So on Cedar, there's 576 4-gigabyte nodes, plus another 182 8-gigabyte per core nodes. Both of those are in CPU-based type of partitions. we have other nodes on Cedar. So there's 16 gigabyte per core nodes, 48 gigabyte per core nodes, and 96 gigabyte per core nodes, or half, 1.5, and 3 terabytes for the different sizes. Now, there's 24 of those nodes of the 16 gigabyte per core variety. There's 24 nodes of the 48 gigabyte per core variety. And there's 4 nodes of the 96 gigabyte per core variety. All 3 of these are basically classified as CPU large for us, large memory nodes. So they're treated as a separate resource. There's also GPU and GPU large, GPU base and GPU large on Cedar with the 114 and the 132 nodes each. These resources are treated with separate partitions. And something similar happens on Graham, except it's a bit simpler. We don't have quite as many different types of nodes for you to think about. There's 804 gigabyte per core nodes. There's 55 8 gigabyte per core nodes. And both of those go into the regular CPU base partitions. They are 24 16 gigabyte per core nodes and 3 96 gigabyte per core nodes for CPU large. And then there's 114 GPU base nodes with GPUs in them. So a little bit about partitions on Cedar and Graham. There's separate partitions for GPUs and CPU requests. So if you request GPUs, you'll be running on those GPU nodes, and they will be requested separately from the way the CPU partitions are. Also, we see here, let's say in the CPUs, we have a by-node partition and a by-core partition. What this basically means is, in the by-node partition is requests that require an entire node. So you're asking for 32 cores on a single node. You could run in the by-node partition. If you ask for 64 cores anywhere on the cluster, you're in the by-core partition. So as you see here, the by-node partition includes all the nodes in the by-core partition. If you want to run on a large set of nodes, on a larger set of nodes, you should be requesting whole nodes. In addition, there's also an interactive partition, so we don't let non-interactive jobs run there. And those are basically set aside for you to be able to run test jobs and test stuff. The purpose of that set aside is that you won't have to wait a very long time for those resources to become available. But this here is the first big outtake you guys should take. So if you're asking for hundreds of cores, what you really should do is ask for a multiple of 32 cores, or at least a whole node. So you should be there's 32 cores in a node. Most of these nodes have 4 gigabytes per core. And if you ask in terms of whole nodes, or you will be able to run with more resources. Same thing with GPUs and whole GPU nodes. But notice that if you ask for a single core job, or just in general lots of cores anywhere on the system, there's a smaller subset of nodes that you could run on. If you have big jobs, you should be requesting it in terms of a set number of nodes. It's actually a little bit more complex than that, because we actually have the CPU base and CPU large as basically their own sets. If you're asking for more than 8 gigabytes of RAM, then per core, you're going to be running in the CPU large subset of nodes, and there's much less of those, by the way, because they're much more expensive because they have to use higher dense memory. And this is done so that those small memory jobs shouldn't be running on those really expensive large memory nodes. But we didn't quite want to have 7 different types of partitions. So we've basically consolidated it into regular CPU ones, CPU base, CPU large for large memory ones, and GPUs. So why did we do this with all this complexity? If we allow zero job to run all the nodes, but then by cores, the chances that there was a node that all 32 cores are not used or coming to an end soon would be very small. So if half the cluster is empty and the jobs are distributed randomly, so each core has an equivalent chance of running a job, of having a job on there, and it's 50%, then the chances that any single node will be empty is 1 over 2 to the 32, or 1 in 4 billion. So even with the cluster being half empty, the chance that any single node would be available for a whole node job would be very small. We did this for this reason, because we need to make sure that people that require whole node jobs, people that run Gaussian, people that run OpenMP jobs are capable of running on the cluster. The same is true if the cluster is full. So if the cluster was full and it had a long wall time, so say we have maximum wall time of 30 days or 28 days in the cluster, the chances that any node will be available within half that time would also be 1 in over 2 to the 32, or about 1 in 4 billion. So people that would like to have a quicker turnaround time also have this issue. So basically, as a consequence, whole node jobs would have to, in practice, wait the max wall time to start regardless of priority. The other part is, if we only allow whole node scheduling, which is done on a large number of clusters, then people that require only one core will take a whole node. And that's quite inefficient. So we basically have to have this complex hybrid approach to allow by core, but only allow it on a small subset of the nodes. What should you be doing? If you can use a whole node, you should be using whole nodes, or multiples of whole nodes. This will allow you to be most efficiently scheduled onto the cluster, and it will get you running quicker. So there's another thing that we did. There are partitions based upon how long your maximum wall time your job has. And your job ends up in the shortest wall time partition that has a longer wall time than your job. Basically, if you're asking for 25 hours, you're going to end up into the 72-hour partition here. So as you see here, the partitions are nested, and they're at 3, 12, 24, 72, 168, which is 1 week, and 672 hours, which is 28 days. As you see here, the shorter wall time partitions include all the nodes in longer wall time partitions. So in this example, if you are asking for a job with 25 hours of wall time, well, it won't fit into the 24-hour wall time partition, so it'll go into the 72-hour wall time partition, and you could run on any of the nodes inside the 72-hour wall time partition. So there's 7 of these. The smallest partition by far is the 28-day long wall time partition. And this is another thing that you could do. So if you can run your jobs in a short wall time, or you can break your jobs up into pieces, this is much better because you could run on much more of a cluster. It's also much better because scheduling shorter wall time jobs is more efficient. We could pack more jobs more effectively together. And there's a big game of Tetris. So if we look what the scheduler does, the jobs often look like Tetris pieces, and the scheduler's role is basically to play with Tetris blocks to make as little spaces, that are empty as possible and as much jobs to run. The shorter your jobs are, the easier it is for the scheduler to actually pack the jobs together. It's also the more responsive the scheduler is. So with more people running shorter jobs, it's more likely that you'll get results back quicker. So that's a win-win for everybody, if you know what you're supposed to do in a cluster like this. Why did we do this? Well, some jobs need to run a long time. So there's commercial code that does not checkpoint. Checkpoints can take a very long time as well. So if it takes a week to checkpoint your job, and 2 weeks to run it, it may not make sense to checkpoint. But if we allow all nodes to run long wall time jobs, it would take a very long time for resources to be available to researchers that need to run shorter jobs, analyze the result, and run another job again. So they would find the system unusable. So if you're a researcher which wants to run for 8 or 24 hours, get the result, and submit another job based upon your result, a cluster that allows a month-long wall time means most users would actually use that. So it would give an advantage. And it would be unusable to you. Yeah, because people that can divide their work in arbitrarily long times would run a long wall time jobs. And as they would have already waited a long time for the job to start. And it would make the situation worse. It would basically cause people to run as long a wall time as possible that's still under the max wall time. And that would make it worse for everybody. So now, Compute Canada has dealt with this situation, and I'm sure that each of the consortia, like Sharcnet, WestGrid, has dealt with it, is by having different clusters, each with different wall times. But there's not enough clusters to do this anymore. The solution is to basically have these concentric partitions on larger clusters to allow us to effectively meet the diverse needs of our user base. These examples are not too complex, but what happens is what's really complex is when we end up doing all these things on the same cluster. So here's a simplified view of that. And it is quite complex when you look at it. So basically here is a representation of what's actually happening with Partitions and Cedar and Graham. So in the top here, we have partitions which are by CPU. And in the colors, they represent how long of a wall time there is for the job to run. So if you're asking for 28 days, and you can run, you're asking for a whole node, you can run in partition A1 here and A2. Capital A1, capital A2. But if you're asking by core, you can only run in A2. If you're asking for less than a week, you could run, and you're asking for a whole node, you can run anywhere within B1 and B2, which includes A1 and A2. But if you're asking for only a core, or by core, you can only run in B2, which includes A2. Same thing with 72 hours jobs. So if you can run it within 3 days, and you're asking for a whole node, you can run in any of the nodes in C1 and C2, which of course includes anything in B1, A1, A2, and B2. But if you're asking for only by core, if you're asking for 200 cores, you'll only be able to run in C2, and so on. So if you ask to run for 3 hours long, under 3 hours long, and for a whole node, you can run on any nodes of that type in the cluster that you ask for. If you're asking for interactive jobs, those are a separate set of nodes. And it was possible that we're going to put in a preemptible queue that if your job can start and stop, and the scheduler is allowed to kill it all the time, so that it could fill in any shaped hole, basically, or in a scheduling system, then we would allow it to run anywhere as well, because it wouldn't be affecting other people if the scheduler is allowed to have other people use those resources the moment your job, the moment they have higher priority than your job. It's actually a little bit more complex than this, because we have basically the high memory and the basic memory, or the CPU large, CPU base type partitions. So there's not just GPUs and CPUs, but there's the CPU large and CPU base, or high mem, basic mem jobs, as we see here in this example. Another thing that we should note is that we also allow some backfill. So we actually allow the shorter jobs in like the 3 and the 12-hour, and even some of the 24-hour serial jobs that require less than 24 hours, we will allow them to run on the whole node area at much lower priority. So that if there isn't enough jobs that require whole nodes, then they will be filled with shorter jobs. Which is also a reason why you should run shorter jobs, because you have more opportunities to run on more of the cluster. So these are really big incentives for people to run shorter jobs, which is good because shorter jobs have less externalities on other people in the cluster. They're easier to schedule, but nicer to the other people using the cluster. Okay, so this is quite a bit complex. And how do you tell what's going on in the cluster? Well, we have a partition stats. So we've written a script, partition stats, which has a whole bunch of information. So in here, we have different categories for 3-hour, 12-hour, 24-hour, 72-hour, 168, and 672-hour jobs. And then we have the type of partition it is, regular, large memory, GPU, GPU large. This is from Cedar. There's a GPU large there. And we have by node and by core. So here we see that there's no queue jobs that are in a 3-hour queue that require whole node, but there's 2 of them that are by core. So they request the resources in terms of cores, and they're less than 3 hours long, and they're asking for regular jobs. So as we see here, in Cedar, there's 559 jobs here that require resources by cores in a 24-hour queue. There's 110 in a 72-hour queue, and so on. So the next column is running jobs, so you can see jobs that are running in each of these queues. What you don't see here is the jobs that are running in a backfill partition. It's the ones that were started because they were quite short and could run in the other resources. What's also happening is that the regular type of jobs are being backfilled to the large memory as well at lower priority. So if there's not enough there's not enough users which are requesting 3 terabyte nodes, will allow the shorter jobs from the regular queue to run on those resources as well. But we'd like those resources to be used by people that actually need 3 terabytes of memory on a node. That's why we don't allow like a 28-day long wall time job to run there, because those resources are supposed to be used primarily by the people that need them. We also have idle nodes by partition type. So this is a really important effect, or really important part of the partition stats script. So here we can see that there are 137 nodes that are available, or that are sitting idle in the 3-hour queue. So they're empty. Now, nodes can be empty for a number of reasons. One reason is that there could be a really large job that wants to start. So let's say somebody requested 5,000 core job to start. Well, it takes a while for 5,000 cores to be gathered. Let's say they have their highest priority, they're going to start, but those resources aren't available yet. So there is a reservation, and the jobs don't start on those resources because we still want those to be available for the new large job to start. So some are sitting idle. Now, if somebody requests a really, really short job, then they may be able to run in those resources, because the scheduling system will know that it won't get all 200 of the nodes idle for another 6 hours. And if your job takes only 3 hours or 5, you can run in that window. So that's another reason why you should be submitting as short jobs as possible. and we see here that there are idle nodes in the 3-hour queue. There's also, and these ones are in the by node. So if you ask by node, you can run on 137 nodes which are idle right now. If in this example, if you ask by core, there's only 30 of the nodes that are idle. But 110 of those nodes, so we see 137 nodes available in the 3-hour queue, but 110 of those nodes are available in a 12-hour queue. These are the same nodes. These 110 are part of the 137. So there's 27 that are only available to the 3-hour queue, plus 110 that are also available to the 12-hour queue. And then in this case, 74 of those 110 are available to the 24-hour queue and the 72-hour queue. And then 19 of those 74 are available in the 168-hour queue. And there's actually 18 idle nodes in the 672-hour queue. So I think this example was taken when they were probably trying to run a 20-node job in a 28-day queue, I think, something like that. It was waiting for enough resources to become available. Same thing's happening for the large memory here. There's basically 2 nodes sitting idle in the 3-hour queue that are available for jobs that request a whole node. But only one of those can be run if you're requesting resources by core. And if you'd like to see how many resources are available in each type of partition, that's the last set of rows here. So there's 691 nodes available in the regular by node 3-hour long partition, of which 317 of them are available if you request your jobs on a by core basis as opposed to a by node basis. But as we see here, if you're asking for 28 days, only 159 of the 691 nodes are available in the regular, for the regular jobs. For the large memory, only 3 of the nodes are available out of the 50 that are available for 3-hour long jobs. So basically, you should be looking at here, and if you can, you should be using whole nodes. You should be running your jobs as short of a wall time as possible, and then you will get access to as much of the resources as possible. You get big boost in the by tailing your job to run in these partitions. And also, while you're doing that, you're making it easier for other people to run as well. So in somewhat of the situations, a win-win is when your jobs are shorter, when you ask for a whole node, it's easier to schedule. It's less likely to have holes in the scheduler. It's more efficient. The system is more responsive. We'll go with one more, a further example here. Partitions and priority example. So this is a particularly degenerate case, but it's illustrative of what can happen. So partition A has a 3-hour wall time, and it includes all the nodes on this cluster. Partition B is the largest partition that your job can run in, and partition C is a subset of nodes in partition B, and contains jobs that have a longer wall time and nodes that can run those jobs. So each green circle represents an idle node, and each yellow circle represents a busy node. So we see here there's 10 nodes. 3 of them are busy on this cluster in this example. So let's assume we have 3 jobs. We have a highest priority job that can run in partition C and requires 4 nodes. Second highest priority job in partition A that requires 5 nodes. And our job in partition B that requires 2 nodes. Job 1, the highest priority job, it cannot run as there are only 3 idle nodes in partition C. Right? And it requires 4 nodes. Job 2, which is in partition A, right? Well, it likely cannot run either. It requires 5 nodes, and there are definitely more than 5 nodes that are idle. There are 7 idle nodes, but it's likely that the first highest priority job has reserved resources, created a reservation. So a reservation is created for the idle nodes in partition C on the first of the busy nodes that would be available. So in this case, we could say, well, maybe in 2 days, one of these yellow busy nodes in partition C will become available for your highest priority job to start. If your second highest priority job has a 3-day-long wall time, it needs to run on one of these idle nodes in partition C. And those idle nodes in partition C, they're reserved. So it's likely that your second highest priority job in partition A won't run either. And if our job in partition B, which is the lowest priority job here, if it requires 2 nodes, and if its wall time is too long, and we've already reserved some of the nodes for the second highest priority job or the first highest priority job, it won't run either. So in such a situation, you can have 3 nodes on a cluster. The cluster is quite empty, but none of these 3 nodes will run. So none of these 3 jobs will run. Now, this is a particularly bad example, but why does it happen? Well, the reason is because the cluster is very small, and these jobs are huge by comparison. So we're talking about jobs that require half the cluster. And the other part is that there are no single node jobs that can fill all these empty nodes, especially because we could have short, single node jobs, and they would run immediately. And this is an example of a worst-case disaster situation. But you sort of have to be a little bit aware of what's going on in the system. The partition stats script is available to you. Just run it. And here it is in Graham. And we can see right now that there are 31 idle nodes that are in the whole node partition for the regular jobs. So if you ask for 3 hours, it's likely that some of those nodes, are being reserved for bigger jobs starting up sometime later, but not all of them. And you're very likely, if you have a short 3-hour-long wall time or less than 12-hour-long wall time, that you will get some of these resources almost immediately. There's something similar happening to the large mem and the GPU jobs as well. You can see how many of the jobs are running and how many are queued right now. So we do see that there are a few queued for some of these. So here, an example, we see that we have 37 jobs that are in the by node partition for the regular type of jobs in a 24-hour max wall time partition. And there is a single idle node. So there's probably a bigger job that requires more than 1 node trying to start here. And there's a similar effect in Cedar. Cedar also has GPU large, which is different from Graham. It also has a number of idle nodes. So if you run shorter jobs, you could actually get more runtime right now. Some lessons. Submit shorter, smaller jobs, right? Jobs that don't require such a big, long wall time. Also, when you look at priority and why your job is not running, look at the priority of other jobs in the partitions that are either the subset or the superset of your jobs. So if you look at your partition and see that your job is the highest priority job in the partition, well, there may be, other partitions that have the same subset of nodes, which have jobs in them that have higher priority than yours. So you have to look at jobs by partition and priority and know that these partitions are subsets of them. Also, this situation in Compute Canada is going to get better. So part of the problem right now is that we have people trying to run very large jobs on Cedar and Graham. And that's because Niagara isn't available yet. So Niagara is the Compute Canada system that's designed for large jobs. With these type of jobs running on Cedar and Graham, it's more inefficient. As we're going to get a more specialized cluster for large running jobs, then the types of jobs on Cedar and Graham are going to get a bit less diverse, and we're going to be able to more efficiently schedule similar and smaller types of jobs on Cedar and Graham. So Cedar and Graham are supposed to be general purpose, and it's going to be easier to schedule smaller jobs when there aren't going to be these big, giant jobs running as often on these machines, because they're going to have their own specialized location. I'm inviting everybody here to go to the WestGrid workshop that's going to be held October 24th. So some of these materials I covered here were originally designed for that workshop, so that's quite a long one. But we start from submitting all the different types of Slurm jobs. We talk about partitions. We talk about all the different types of resources. We talk about priority, how to find out what's wrong with your job, how to fix problems, and so on. And I'd like to invite everybody as well from here in Sharcnet that you're also welcome to all the WestGrid training events, which are available. You can see here.